Good afternoon, everybody. My name is Joseph Patton, and the paper that I reviewed is called A Deep Neural Network for Unsupervised Anomaly Detection and Diagnosis in Multivariate Time Series Data. This paper was authored by Zhang and colleagues. First, as an introduction and a motivation for this project, complex systems such as power plants, IT systems, or even spacecraft can generate many different types of time series data. For example, in a power plant, you might have voltages, currents, temperatures, and even pressure that is measured in the power plant to ensure that the system is healthy. If one of these signals presents an anomaly, then it's critical that you can detect the anomaly as soon as possible to ensure that the system doesn't enter an unhealthy state, or that you could shut down the system and maybe mitigate the anomaly somehow. So the two main thrusts of this paper are anomaly detection. So firstly, where is the anomaly? If you look at the image in the middle of your screen, you can see 4 time series datas, and A1 shows an anomaly in that data, and then A2 also shows an anomaly. So trying to determine where in time these anomalies are is our first problem. Our second problem is anomaly diagnosis. So if your system enters an anomalous state, how do you figure out which time series is likely to be causing the anomaly? So the solution to these problems is presented in this paper as the MSCRED Framework. So firstly, we start by encoding the time series data into what we're calling system signature matrices. Those matrices are then encoded using convolutional steps. The data from the convolutional encoding is then passed into a convolutional long short-term memory stage, and then finally the data from the convolutional LSTM is decoded in a deconvolutional stage. Then we take the reconstructed signature matrices and take the difference between those and the original matrices, and we're left with our residual matrices, which we can then analyze to detect anomalies. So first, how do we characterize the system status with signature matrices? So at the top of your screen, you can see 2 examples of signature matrices for our time series. So basically what this allows us to do is to mix our time series data into a 2D representation that can be passed into our convolutional encoder. So the intuition behind using these signature matrices is that correlations between pairs of time series are important to characterize the system status. And what these signature matrices basically represent are just correlations between our time series. And we calculate that by using an inner product between the time series. So if you look at the images on the bottom right, the bright red portions indicate places where the time series had high correlations, and the darker blue areas represent where there were lower correlation. So basically, by using these 2D representations, we can capture shape similarities and value scale correlations between our time series data. Another important feature of doing this sort of correlation is that it's very robust to input noise. If you're using long vectors of data, for example, like 30 steps for your time series data, and then calculating the correlation, one noisy point in either data, it won't affect the overall correlation very much. As you can see in the equation, the final thing we do is divide that inner product by k, where k is simply the length of each time series data. So in the paper, they encode 30 by 30 signature matrices. So that represents a system that has 30 different time series. The groups of 3 signature matrices that you can see in the bottom figure represent 3 different timescale depths. So what that means is we're looking at the previous 10 time steps, the previous 30 time steps, or the previous 60 time steps when we're calculating these correlations. And what that allows us to do is to find anomalies that are at different time durations. So by default, the distance between each signature matrix is 10 time steps. And what that means is if you're doing a depth of 10, then the signature matrices won't overlap. If you're doing a depth of 30 or 60, then they will overlap. So next is the convolutional encoder. So the convolutional encoder looks at the spatial patterns of the correlations of the signature matrices. And in this case, the order of the time series is actually not important. Any permutation of the time series that you do, the spatial patterns will still be captured. So if you, for example, were looking at voltage, current, and temperature, any permutation of those three things could be built into the signature matrices, and this process would still work. So we have 4 stages here in our convolutional encoder. So our first stage, we have 32 kernels, then 64, then 128, and finally our 4th stage of convolution has 256 kernels. So next is our attention-based convolutional LSTM. So originally the convolutional LSTM was developed to capture temporal information in video sequences. For example, if you have a ball moving across a screen in different frames of a video, the convolutional LSTM can focus on this sort of feature. But in this work, the convolutional LSTM was actually modified, and they added an attention-based mechanism that can select just the relevant feature maps across time steps instead of weighting them all equally. And the reason that we're using a convolutional LSTM is it allows us to jointly model the spatial patterns of the correlations of the time series as well as the time-based information in the time series. So firstly, just the difference between the convolutional LSTM and a regular LSTM. So in a regular LSTM, we'll have matrix multiplies, and eventually the dimensionality of our data will be reduced. But in the convolutional LSTM, we replace the matrix multiplies with convolutions, and this allows the output data to have the same dimensionality as the input data. So some of the motivations of using attention in the convolutional LSTM. So firstly, according to the authors of this paper, the convolutional LSTM performance will degrade as the length of the input sequence increases. Another motivation from these authors is that not all the previous time steps in our time series data are equally correlated. So by using temporal attention, we can emphasize the most important, most correlated time steps in the past. So we do that by the bottom equation that you can see. So we have these alpha values that we multiply our time steps by, and these are importance weights. So we simply calculate these importance weights by using the softmax function that you can see on the right. So we take an inner product between our current time steps and previous time steps, and the time steps in the past that have the highest correlations are assigned higher importance weights. So next we have our convolutional decoder. So once we've done our convolutional LSTM and we've assigned our importance weights to get our attention, then we decode the data. So each deconvolution layer is actually stacked with the output of the previous convolution LSTM layer. And that's one reason that we used a convolutional LSTM, is that we could retain the dimensionality of our input, and then it fits the dimensionality of our convolutions, and we can concatenate them together. So this step improves anomaly detection performance because we're incorporating the feature maps at different layers. So as you can see, we actually work the process backwards from our encoding layer. So our deconvolution 4 step has 128 kernels, our 3 step has 64, then 32, then finally 3 kernels in our deconvolution 1 step, and now we're back to signature matrices. But the difference is that these signature matrices are reconstructed. So now onto our loss function. So the loss function in this system is actually very simple. we just look at the reconstruction error in our signature matrices. So we just take the difference between the original system signature matrices, our reconstructed matrices, and then we are left with a residual matrice. So the assumption here is that when you're reconstructing your signature matrices trained by your network, those represent nominal behavior of the system. So if there's any difference between your input matrices and your reconstructed matrices, then that must be anomalous data. So our next step now is to do anomaly detection and diagnosis with our residual matrices. So first, anomaly detection. So how do we use these residual matrices to find anomalies? So this is also pretty simple. We have a method called the anomaly score. So the anomaly score is simply the number of elements in the residual matrix that are above a certain threshold. And that threshold is set with the equation that you can see there. So we have tau is multiplied beta and the max value of ST valid, where ST valid are the anomaly scores calculated over a validation period, and beta is a constant value that you also calculate during validation. So next on to anomaly diagnosis. So how do we figure out which time series is most likely to cause the anomaly? So we basically just rank each time series by its anomaly score. So as you can see in the figure on the left, the different rows and columns of our residual matrix represent contributions from the corresponding time series. So at the top we have 0 in our row, and at the bottom we have 35. So if you have high values in those rows, then those anomalous data points are said to be caused by those time series. The plot on the bottom of the screen has anomaly score over time, and the red dotted line represents our threshold that we discussed in the last slide. So basically, whenever we have an anomaly score that's over that threshold in time, we're said to have an anomaly. And then finally, the highest scoring time series, the time series that has the highest anomaly score, is said to be the largest contributor to the anomaly. So in this case, you can also discern anomalies that are caused by multiple time series, and you just rank them. So next, on to the experimentation. So how did they characterize this network and show that it was producing desirable behavior? So there are 3 experiments that were conducted because they wanted to characterize the following 3 elements of the network. So firstly, as mentioned before, we want to see anomaly detection. Second, we want to see anomaly diagnosis. And finally, we want to look at the robustness to noise of the network. So the network was tested in 2 ways. First, they used a synthetic data set, and then they actually used real-world data from a real power plant. So first, the synthetic data. So the synthetic time series were calculated using the equation on the right. So we have some sinusoidal expressions, and they're added to that lambda times epsilon, which is Gaussian noise at different amplitudes. So they randomly selected these sines and cosine functions with random periods and random Gaussian noise, and generated 30 sinusoidal time series, and they have varying correlations based on these parameters. So what they did was they took 20,000 data points for each signal, and then artificially injected 5 anomalies into 3 of the signals. So that way they could detect, they could try to do detection as well as diagnosis. Next is the power plant data. So the power plant data, which was real world, had 36 time series generated by sensors that were within the power plant system. They had 23,040 time steps with 1 real anomaly. And to improve the testing, they also injected 4 random anomalies during testing. And you can see a side-by-side comparison here of the synthetic data and the power plant data. So the same number of anomalies, the same number of root causes, and then the training, validation, and testing period were about the same order of magnitude. So now to look at some of the baseline methods that they compared MSCRED to. So because MSCRED was performing a few different functions, they actually compared them to a few different models in different categories. So firstly, in the classification category, they compared MSCRED to the one-class SVM model. Next, in density estimation, they compared MSCRED to deep autoencoding Gaussian mixture model. Next, in the prediction category, they compared their model to history average, autoregression moving average, and finally STM encoder decoder. And also to validate some of the different features of MSCRED, they compared regular MSCRED that you saw the framework of to MSCRED with certain components removed. So firstly, they have MSCRED with the attention module and the first 3 Convolutional LSTM modules removed. Then they removed the attention module and the first 2 Convolutional LSTM. And then finally, they tried just removing the attention module. And this is just to see, are these modules helping at all? Are they performant, or are they just unnecessary? So next, on to training and their evaluation metrics. So they implemented MSCRED in TensorFlow. They trained it on an Intel Xeon processor, and they had 4 NVIDIA 1080 graphics cards. The evaluation metrics that they used are precision, recall, and F1 score. And if you recall the anomaly threshold value that equation that we looked at before, the beta value was actually set during the validation period just to maximize the F1 score. And then the same beta value was just used to calculate the precision and recall as well. So now on to the performance evaluation. How did MSCRED do with anomaly detection? So looking at our table on the right here, MSCRED shows an improvement on all of the baseline methods. And it also accurately models our temporal patterns and trends that arise from our inter-sensor correlation. And then if you look at some of the reduced versions of MSCRED where they took out different modules, those are less performant. And as you increase the layer of the number of convolutional LSTM layers, then your performance increases. So that sort of validates the network and shows you really do need all those parts. And the bottom row shows the gain in our different evaluation metrics that you get over some of the other methods. So next, some more anomaly detection results. So what we're looking at here are the anomaly scores generated by some of our baseline networks versus the anomaly scores generated by MSCRED. And you can see, for example, in the left column, looking at our synthetic data, the anomaly scores generated by ARMA, they're much noisier. And we also have some, for example, some false positives and some false negatives. The blue columns that you can see represent true anomalies, and the red dashed line again represents the threshold of the anomaly score generated by these networks. And if you look down at MSCRED, the anomaly scores are quite noiseless, and there are also no false positives and no false negatives in the synthetic data or the power plant data. So next, on to anomaly diagnosis. So we've already talked about how the anomaly diagnosis works. So different time depths, as well as anomaly diagnosis, using our 3 different depths of network, 10, 30, and 60, different time depths of anomalies can be detected. So, for example, the large MSCRED network might miss some of the small anomalies but catch the big ones, and the small network will catch different sizes of anomalies, and by comparing the different sizes of networks, you might be able to estimate the time duration of an anomaly. And then, as we've said before, just by ordering our anomaly scores, you're able to determine anomaly root cause. And then finally, our last performance evaluation is robustness to noise. So by varying that Gaussian noise parameter in our synthetic data, we're able to increase the amount of noise introduced into our data going through our networks. And on the right, you can see that MSCRED shows the least amount of performance degradation when you increase the noise. So it outperforms LSEM-ED as well as ARMA, which were some of the more performant networks in the baseline. So in conclusion, MSCRED was presented in this paper, and this model is useful for detection and diagnosis of multivariable time series data. It does that by leveraging correlations between our time series data, but also by looking at the temporal dependencies. So in this paper, MSCRED was tested on synthetic data and real-world data, and in both cases, it was highly performant. If you're interested to see some more of the details of this paper, it's available at this link. Thank you very much.